Okay, in this video then we are going to expand on the idea of two-source interference that we looked at in the previous video and look at this very, very famous and important experiment which was carried out back in the early 1800s by Thomas Young. Now the experiment is called Young's double slit experiment, and you will see why in a second, and it's using that idea of two sources of waves which are interfering with each other. So let's think of the basic idea behind this experiment. Essentially, what we have is we have some light, and we pass that light through a double slit. So in other words, two slits close together. And then a certain distance away over here somewhere, we have a screen. Now, there are a few things to to consider here. Firstly, over here I've been quite general with this word light. Now remember, in order for us to see the interference effect, we do need the two light sources to be coherent and monochromatic. So really we could do with monochromatic light here. Now, you might be saying, well, where are the two sources? I've only got one source of light. Well, yeah. This double slit is creating, effectively, two sources. So once the light goes through the double slit, you can consider each slit almost as a source of the light. Now, in order to make sure those are coherent, there are two possibilities. And the most common one here is actually, instead of just having light in general, is to use a laser. And the reason for that is that lasers are not only monochromatic, but also you will get a coherent beam of light, therefore you will get two coherent sources at this point. So a laser beam is the best way to do this, having a laser beam hitting the double slit, and then we see what happens. Now if you don't have a laser, another way you can kind of try to ensure coherence is actually to put a single slit in here first. So that almost gives you a very, very small point source almost of light, which will ensure coherence. So you can use a single slit to ensure coherence. Okay, hopefully you can read that. Now, let's think about what you would expect to see. Well, your average person, if you ask them, well, what will we see if we do this, would say to you, well, you'd see a blob there and a blob there. You'd see two blobs of light on the screen because one through one slit, one through the other slit. But hopefully you can see from what we talked about before that actually what you would expect to find, let me just get rid of those, what you would expect to find is a series of maxima and minima. Okay, the red dots there representing maxima because light here is going to interfere. Okay, you get interference occurring, and so what you see is what we call a fringe pattern. And from what we saw before on the first diagram, that's going to consist of equally spaced bright and dark fringes, which in reality will just look like lines essentially. Fringes just meaning like a line of light. Okay, and the reason for this, if we just go back to our diagram from the last video, we're essentially putting a screen kind of here. And so you're seeing constructive, so maximum, destructive interference, minimum, and so on. Okay, and so what we see on our screen there is the bright and dark fringes. Let's take a look at that. Let's actually have a look at that in reality. This is a laser, and that is pointing at here some double slits. Now, you can't really see, okay, but actually there's a very, very, very close together. There are two double slits, and in fact, they are 0.1 millimeters apart. And what I'm going to do then, I'm going to shine that through the double slit and onto the wall, and we'll see what pattern we see. Okay, so what you can see there, that is the wall about a metre or so away from the double slits that I just showed you. So if I turn my laser on, we are expecting to see bright and dark fringes on the wall there. Okay, so if I turn my laser on, there it is, and you can see there, okay, the bright and dark fringes. Now, they're not equally bright, which we were expecting them to be. There is a reason for that, which I'll come on to in a future video. But there in the centre, there's the first fringe, there's the second fringe, third, fourth, fifth, sixth, and so on. Okay, so you can see there that we've got the fringes like we expected. Okay, so now you've seen what it actually looks like, we're going to have a look at the formula which we need. Now, I'm going to show you the derivation quickly. You don't need to know the details of the derivation, but I do think in this case it's useful for you to have seen it. So what I've got then is over here, I've got my double slits, and we are calling the distance between those S. And then over here I've got my screen, and I'm saying that the distance between the slits and the screen is capital D. Okay, now we know from what we just said and what you've just seen that what we are going to actually see in this case is some bright fringes. Okay, and so we're going to have one right in the middle there, and then we'll have a series of equally spaced bright fringes. Now let's imagine the first bright fringe up from the middle line. Okay, they are supposed to be equally spaced. I appreciate mine is not drawn particularly well. So let's just draw in quickly. I'm going to just draw a horizontal line across. That's showing the middle, really. And then let's imagine this first bright fringe up. Okay, now I'm going to just call this angle in here theta. Now let's think about what's actually happened in order to get that first bright fringe. Well, we've got light from this slit here, and we've got light from this slit here, and they are interfering. Now, in order for us to get this first bright fringe, okay, we know that the path difference must equal lambda. Because for the central bright fringe, that's where you've got 0 path difference. First bright fringe, that's lambda path difference. Second bright fringe, 2 lambda path difference, and so on. Now, looking at our diagram, let's think of how we could actually draw the path difference. Well, the path difference is going to be, if I imagine that I'm drawing a line down from this top slit, and I'm basically making a little right angle triangle here. Okay, that's making a little right angle triangle. This distance here, that green line, that is the path difference. Okay, because what I've now got, my 2 red lines remaining are now the same length. And so this little green line, that's the difference in path length between the bottom line and the top line. So therefore, that is lambda. That green line is lambda. Now, I've got a right angle in here. And this is where we have to use some approximations. And this is actually where I come back to those approximations we said right at the start of the last video about small angles. So I've got my angle theta here. Now very, very roughly, I just draw another line across. This is another horizontal line. Very, very roughly, that angle in there is also approximately theta. Now, this is using the assumption, very important assumption, that D is much, much larger than S. So in other words, the distance from the slits to the screen is much, much bigger than the separation of the slits. And that will normally be true. You know, we're talking about slits like 0.1 millimeters apart. So you will find this is true. Now, if that is the case, if those two angles are the same, that also means that this angle here is theta. So the angle in between the black line and the green line is also theta. So let's have a look then, first of all, at the blue triangle. So there, there, there. For that blue triangle, okay, we can say that tan theta equals opposite. Well, the opposite here is the the fringe width, and the fringe width here is usually given the letter W. That's really not very clear, is it? Let me write it again. W. Okay, so we know that tan theta is opposite, that's W, over adjacent. The adjacent here is D. For this green triangle, so there to there to there, we know that sine theta equals opposite, well that's the path difference, which is lambda, over the hypotenuse, which is this edge, hypotenuse is S. Now for small angles, tan theta equals sine theta. So therefore we know that W over D equals lambda over S. And therefore W, so that's the fringe width, is lambda D over S. And that is our key formula for the Young's double slit experiment. Okay, now it's, as you can see, it's a relatively simple formula to use once you've got some numbers, but you do need to be aware then of how to use it. All right, now you've seen the formula then, let's see if that formula can tell us anything or make a few predictions. So there's our fringe pattern again that I showed you earlier. Now let's think about what the formula predicts if we change the wavelength of the light. Well, I've got a green laser as well. Now green has got a shorter wavelength than red. So if I change to light of a shorter wavelength, our formula predicts that W should also get smaller, because W is lambda D over S, so smaller wavelength should give us a smaller fringe width. So I'll show you the red again, just to give you a sort of reference. There's the red, okay. And what I'm going to do now then is switch to the green. There's the green, and you can see there, okay, they are much closer together. I appreciate it's not that clear on the screen, or on the camera, sorry. In reality, it is much better, but you can see that they are closer together. Okay. Now, there are other things we could change. Let me just go back to the red. There's the red again. We could also change the slit separation. So W is lambda D over S. And so if I change S, I should also change W. So this is with a slit separation of 0.1 millimeters. That's the pattern we get. I'm now going to change to a slit separation of 0.5 millimeters. In other words, S is 5 times bigger. Now from our formula, that means we should expect W, as our fringe width, to become 5 times smaller. So there's one final look with the 0.1 millimeters. Okay, now I'm going to quickly switch across to 0.5 millimeters. And there you go. Now, actually, the fringes there are so close together you can barely see them on the camera. Okay, but they are there, and they are most definitely closer together, just like we would have expected to see. Now, everything we've said so far has been for monochromatic light, so let's just think very quickly what we would find if we were not doing this with monochromatic light, but we're doing it with white light. Well, white light is obviously made up of the whole spectrum, and so you saw a minute ago that the fringe separation depends on wavelength. So if you do this with white light, each wavelength that's within the white light will have a very slightly different fringe separation. And so what you will end up seeing is the following. So you'll see a central white fringe because all wavelengths have that maximum in the middle. But then you can see as you get further out, you start to see a separation of the colours. And so you won't see distinct fringes. You'll see more blurred fringes, and you will see the different colours, the spectrum, start to become visible there.